So we ended on this problem 3 last time. So let's just finish up these last 3 here. So number 4, we have a product of essentially this 3x squared plus 5x and this e to the x. So again, remember, I kind of just like splitting it up and getting all of my pieces before I piece it together. But however is best for you. So remember, we need, so essentially the derivative in general here is going to be our f prime g plus fg prime. So we need kind of all those pieces. So if I have that f is 3x squared plus 5, then our f prime would be 6x plus 5. And if g is e to the x, then g prime is also e to the x. So if I put that together, we have f prime. Remember, if any of your pieces have addition or subtraction in them, you should put them in parentheses, or else it's going to be wrong. And then so we have f prime g times f g prime. Now in this case, of course, that would be perfectly enough. We don't have to simplify. I never ask you to simplify these. I am going to do one thing to simplify it, though, because it's going to be helpful when we get into chapter 4. So I kind of want to do it as like a somewhat preview kind of deal. Yeah. Ooh, that one's lagging a lot. Ooh, it's making me lag a lot. That was fun. And just in case anyone else is lagging as much as I want, I'll wait. Come on, you can do it, little computer. Here we go. So what am I doing? I'm doing one tiny thing of kind of simplification. Note that both of those terms have an e to the x in it. So what I can do is I can factor that e to the x out. And I'm going to leave like too many parentheses. We technically don't really need this many parentheses, but just to try to help show what happened, I'll leave the parentheses on those terms there. We get this. And then reshare it again. Okay. I just did, but I can do it again. Now I gotta wait for that one because it's lagging a lot. There we go. Brain. So the only other thing we could do here is we could kind of combine together those things on the inside now. So we would have 3x squared, the 6x and the 5x would combine together to give us 11x, and then plus 5. I also like to put them in order of their powers. But so again, this line here is perfectly acceptable for just finding the derivative. Again, this kind of extra step is going to be useful once we get into chapter 4 because we're going to need to be doing more with these. But yeah. So hold on like a couple seconds because I know some people needed it to be reshared. So I'll give you all a couple seconds to catch up before we go on to the next one. Do. 5 more seconds. Okay. I gotta scroll back up a little bit. I'll just zoom out a little bit. There we go. Now we can keep everything on there. All right, cool. So jumping over to number 7. So now we have a why my word's not working. Quotient rule. Remember, let me scroll up really quick. Remember that you can kind of always change the quotient rule into a product rule if you want. That's what we kind of did with this very first one up here, where you just take the denominator and put it to the negative first power. This one would kind of be one to do that with because the numerator is just 1. I'm going to use a regular quotient rule, but just in case you're one of those people who really likes to use the product rule instead when you can. Well, in fact, this case, it wouldn't even be a product rule because if you were to use that, what would happen is you would have that f of x is 1 plus e to the x to the negative first, and that would actually just be a chain rule. It wouldn't even be a product rule. But anyway, Let's do a quotient rule on that. So our numerator is 1 and our denominator is 1 plus e to the x. So we have our f and our g. And we're going to need g squared in this case, because remember the derivative of the quotient rule gives us that over g squared. So what's the derivative of 1? It's 0, because 1 is constant. It's the derivative of 1 plus e to the x. That's going to be 0 plus e to the x, so I'll just write e to the x. And then g squared, 1 plus e to the x all squared, and just leave it like that. 1 plus e to the x all squared. So then putting it together, we'll need f prime g minus fg prime all over g squared, just to remind us. So f prime, I'm going to write it out in full generality, even though we've got zeros floating around. But so it would be 0 times 1 plus e to the x minus 1 times e to the x all over 1 plus e to the x all squared. So if we simplify this down the tiniest bit, we get negative e to the x 1 plus e to the x all squared. Essentially getting rid of that 0 times term in the front. There. All right. As always, I'm just kind of pausing afterwards in case any questions come up. For this last one, we have that essentially our numerator is e to the t, denominator is t squared. So we have our f and our g. So f prime would be e to the t and g prime would be 2t. Oh, it's lagging a little bit. There we go. And g squared would be t squared all squared. Now that one is simple enough that you should really simplify that down to t to the 4th. If it's something like 1 plus e to the x all squared, you can totally leave that. But when it's something like just a singular term squared, just go ahead and square it. I wouldn't take points off if you didn't, but technically it's easy enough to simplify that, so you probably just should. So if we put this together using our quotient rule, we have f prime times g minus f times g prime all over g squared. Again, I'll take the time to simplify this really quickly. There's not too much to simplify here, but one thing I'll note, it wouldn't even really be helpful for the next section, but I'll just do it anyway. Notice that every one of the terms in the numerator and the term in the denominator have t's. And specifically, they all have at least one. So essentially what could happen is we could essentially factor that t out of the numerator. And I like writing the e terms in the back, so that's just personal preference. If you kept it as e to the t times t and e to the t times 2, that's perfectly fine. And then you think of the denominator as t times t cubed, and then those t's can cancel. And we get t e to the t minus 2 e to the t over t cubed. Again, not really necessary, even for chapter 4, that doesn't really help out as much. But technically, we will be doing a bit more simplification in chapter 4 because of the algebra we'll have to do afterwards. But this line here is perfectly acceptable for a generic derivative. Any questions or concerns on those generic product or quotient rules before we move on to the ones that look a bit different, the ones with just the generic format or plugging in the numbers? I'll wait 5 seconds. Okay. Sorry. Moving on then. So we've got to hit the things that, scroll down please, that we didn't get last time. So I know we jumped around a little bit last time. So let's start with these problems 8 and 9, which are about finding tangent lines. Now, technically, we found tangent lines in chapter 2. It was just that we had to use the instantaneous rate of change instead of finding the derivative exactly. Now, the thing I'm about to write down This is technically from chapter 2 notes. So I'm going to write it down very quickly. We had the process in our chapter 2 notes, but let me just remind us of what that process is. So we're going to find the derivative. We're going to plug in the x value to f of x. This is going to give us the point for our equation. And f prime of x is going to give us the slope for our equation. And then use chapter 1 material to write y equals mx plus b. So again, we technically already have that down kind of in a bit more official notation in chapter 2, but just to remind us of what we're doing here. So we want to find a tangent line. So I'll wait 5 seconds in case people are trying to write that down. Again, we have it, but maybe someone wants them here too. But unlike in chapter 2, we can actually find the actual formula for the derivative. So that's what we're going to use instead of having to estimate using the instantaneous rate of change. So find the derivative. Derivative of x cubed, bring the power down, subtract 1 from the power. We have 3x squared plus 4x minus 5. So now we want the tangent line at x equals 1. So we're going to essentially take that value of 1 and plug it into both the original function and the derivative. So essentially what we're going to want to find is we're going to want to find f prime of 1 and regular old f of 1. Since anything times 1 is itself, we essentially just get the coefficients here. So it'll be 3 plus 4 minus 5. So 7 minus 5 is 2. And then when we plug it into the original function, we'll get 1 plus 2 minus 5 plus 7. So 1 plus 2 is 3, plus 7 is 10, minus 5 is 5. So essentially what we've done is we've given ourselves the slope of the tangent line and a point that we can use to find the b value of the tangent line. So, sorry, I never know how long to pause because I can't just gauge it on when you guys are done writing. So we want some y equals mx plus b. So we have y is 5, m is 2, x is 1. We need to solve for b. Subtract 2 from both sides, you get that b is 3. So we get y equals 2x plus 3 as our tangent line. Okay. For the next one, it's very similar. Let me try to scroll down a little bit. Kind of that last half in there. Oh my goodness. There we go. Same kind of idea, just a slightly more difficult function because we have a chain rule going on now. But same idea, we want to take the derivative first. So since we have a chain rule and the outside function is that natural log, first piece is we're going to have 1 over 2x plus 3, because remember the derivative of the natural log of something is 1 over that something, times the derivative of the inside, which in this case is the 2x plus 3, derivative of 2x is 2, derivative of 3 is 0, so I'm just going to erase that and just put the 2. Once you've found the derivative, you then want to plug in the value that you want the tangent line at, and you also want to plug that value into the original function. So since we want the tangent line at -1, we're going to use -1. So if we plug in -1 to the derivative, we'll get 2 over -2 plus 3. So 2 over 1 is 2. And then if we plug -1 into the original function, we'll get natural log of -2 plus 3. So the natural log of 1, which is 0. So again, now we essentially have that our slope is 2, and we have a point that we can use to find the equation of the line. Plug that into y equals mx plus b. So we've got 0 equals 2 times -1 plus b. Add 2 to both sides, you get b is 2. So y equals 2x plus 2. Questions, concerns about either of those? I'll wait 10 seconds. And don't think you can't ask me to go back afterwards. I'm just giving myself a time frame before I call it okay and move on. All right. So that's how we find tangent line. No matter what, always the same process. The derivative in the value, plug in the value to the original function, equals mx plus b it. Oh, Delaney, I did a little rewriting that I guess I didn't kind of note. I rewrote as 2 over 2x plus 3. So the 2 that was originally being multiplied on the outside got pushed up into the numerator. Sorry, I didn't really say that I did that. But that's why, because I think that's what you're getting at. So it is being multiplied by 2 in a way, just not how you might have wanted it to be. So blah, 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 blah. Essentially, if I were to write it like this, I would have had 1 over -2 plus 3 times 2. So 1 over -1 times, nope, positive 1. Okay, cool, Delaney. Haley, so there's a, how do I explain this? So yes, the derivative of the natural log of x is 1 over x. Totally agree with that. Notice that here it's not just an x, it's 2x plus 3. So what we have is we actually have a chain rule here. So with chain rule, remember that essentially tells us that we need the derivative of the outside multiplied by the derivative of the inside. So essentially what's happening, you know what, let me just erase this really quick. And now that I don't have any more orange, I guess I should erase the orange. So my outside function here is the natural log. So I do want to use that natural log rule that says the natural log of, now here's where it gets more complicated, because with the chain rule, you should think about it as something like natural log of something is 1 over that something. So whatever you have in that natural log is what goes in the denominator. So our derivative here will start with 1 over 2x plus 3, because that was the thing inside of the natural log, and that comes from, you know, this rule over here. Whoa, why do you do that? But then the chain rule says that we then need to take the derivative of that inside. We need to take the derivative of the 2x plus 3. And that gets multiplied to the end of our function. So the derivative of 2x is 2. And then we have to add on the derivative of 3, which is 0. And I just didn't write the plus 0. So Haley, yes, while you are thinking about the derivative of a natural log thing correctly, you're forgetting to bring in the fact that this is actually a chain rule, and that the chain rule kind of messes with all types of different functions. Yeah. Yes, Exactly, Haley. So if that was the natural log of 2x instead of 2x plus 3, the same thing sort of would have happened because we still need to take that derivative of that 2x, which gives us that 2. Exactly. Any more questions? Okie dokie. So last time we did jump to problem 10, so we did do that one already, so we're not going to do it again. But just to remind us of what this was, we were finding the derivatives generically, and then we were just taking the values that were given and plugging them in. Also remember, I really like these types of problems. Nudge, nudge, wink, wink. So might want to look them over if you're still struggling with them a little bit. But we do have 2 more like this. They're just going to be product and quotient rule instead of chain rule. And these types of ones do show up on your homework. So yeah, anyway. So we didn't get to this one the other day, so let's go ahead and do this one. So it's essentially the same type of idea where we're going to find the generic derivative and then just plug in the values using what we're given. So we're told that the first thing we want to find the derivative of is essentially this product of 2 functions. So we know how to find that derivative because essentially it's going to look exactly like the product rule. Now be careful because you don't want to think that you couldn't have taken that, say this was an A and a B instead of an A of X and B of X instead of F and G. Use that same format. So we need the derivative of the first function times the original second function. So we have F prime of X times G of X plus the original first function times the derivative of the second function. So F prime of X times, sorry, F of X times G prime of X. And then we're going to plug in a 2 everywhere we see an X. And then colors. So we need F prime of 2, which will be equal to 5. Let me just do all these in colors really quick. G of 2, which will be 3. F of 2, which is 1. And G prime of 2, well, I already used blue. Purple. G prime of 2, which is 6. So if we replace all those values where they need to go, we've got 5 times 3 plus 1 times 6. So 15 plus 6 is 21. All right. I'll hold on for 5 seconds. So then the other one is essentially now instead of multiplying the 2 functions together, we're going to take f of x divided by 2x. So again, first thing we want here is just the generic derivative. So we want to just essentially follow the pattern of the quotient rule. So we need the derivative of the first thing, the derivative of the numerator, times the denominator left alone, minus the numerator left alone times the derivative of the denominator. I'm kind of phrasing it like that. I'm avoiding saying f prime and g because again, these don't have to be f of x and g of x. They can be absolutely any function with any letter that you want. Divided by the denominator all squared. Plug in a 2 everywhere you see an x. And let me take a second to color these again. So we have 2. And then g of 2, but g of 2 also turns up in the denominator. F of 2 and g prime of 2. So we've got 5 times 3 minus 1 times 6 all over 3 squared. So 9 over 9 is 1. Questions, concerns on either of those? I'll wait. Sure. I know exactly what you're talking about. Scroll up. Oh my God. So there's one on your homework that includes a square root. I think it's an R of X. It might be an S of X. I don't remember. But essentially, you want to find that's going to be defined as H of X. And then, again, I don't remember the actual number, but I think it might be 2. You want to find the derivative of that evaluated at a certain point. So the one thing you want to do here is that you want to recognize that the square root is equivalent to a 1/2 power. So if this is equivalent to the original equation X, then H prime is essentially going to be a chain rule. So you need to bring the power down and subtract 1 from the power, but leave that R of X alone. And then multiply by the derivative of R of X. Now, someone else was having trouble with this inputting the answer, even though she had the right derivative. So let me triple check how Wiley wants their answer. Really quick, so give me 1 second. Because at this point, what you would do is you would take all of those X's, turn them into whatever value they gave you. I forget. I think it's a 2. I'm about to pull it up in a second. So, I didn't change that other X. Super quick. This one. No, this one. Oh, well, now see, the question I pulled up might not have the same values as the question you guys have, but essentially the question I just pulled up has 6s here. And the things that I would need would be so here Wiley has them input as a fraction. So you probably, it might not accept decimals. So what you would want to do here, I've run out of space. So in my case, this is what I'd have to the negative 1/2 R prime of 6. So I'd have 1/2 times 16 to negative 1/2 times negative 1. Now, I gotta go back this way, sorry. Now the negative 1/2 power would essentially make that 1 over 16 to the 1/2, which is equivalent to the square root. So you'd want to think about it as 1/2 times 1/4 times negative 1. So my answer would have been negative 1/8. And I would have wanted to put it in as that into Wiley, which is equivalent to negative 0.125. But again, I don't know if Wiley's accepting the, those are not. Catherine, my numbers might be different than yours because I just pulled up a random one on Wiley. That's the numbers that the question that I pulled up on Wiley had. You might have different ones. But in my question, I'm told that R of 6 is equal to 16. So I'm taking the R of 6 that I started with and replacing it. It did work for you when you used the fraction? Okay, yeah, I don't know if it's being weird. It should definitely accept the fraction because that's what they have in their solution. It might be weird with decimals, I don't know. So just in case. So that's how that one goes. All right, So I'll leave that up for 5 more seconds, then we'll move on. Actually, well, we can move on, but and I am going to erase it because I don't want anyone looking back at this and thinking it's part of some of the problems that are here because it's not. So if you want to snap a picture real quick, I'll give you 5 more seconds, but you can always just go back at the recording and find it. Anyway. All right, it's going away now. Bye. Whee! You can find it in the recording later. But I will post by the end of the day. Race. All right. We did all of this one the other day. There's something I want to say really quick about your homework. I want to gravely apologize for the ones that included these. I'm really sorry. My one screen doesn't even have it up there yet. So there were 2 multiple choice ones that included these graphs, and it was my first time assigning this particular question, and they were harder than I thought they were. So I just want to apologize for those. They work in a very similar way where you essentially find the generic derivative and then you're looking at slopes of tangent lines, but finding the slope of the tangent line is what's really tricky with these because the graphs aren't very nice. So I apologize for those. Try your best. They're multiple choice, so worst case, just guess. Really super apologize for those. I will say, so there was another one that essentially had straight lines. I don't apologize for that one. So the ones with straight lines are better because you can actually find the slope easily because it's a straight line and it's given to you as a straight line. So if on a quiz or an exam I were to give you a question with graphs, it would be something in terms of straight lines that you can actually find the slope of easily, and not like those multiple choice from the homework that it was really hard to find the slope of the tangent line. Again, sorry, did not realize those were as complicated as they were when I assigned it. But anyway, we did those yesterday. Not yesterday, you know what I mean. For the sake of time, I'm actually going to skip these last 3. Now don't panic. These 3 are exactly like things we did in chapter 2. It's just that we were actually going to find the full derivative function before doing the chapter 2 stuff. I will write up the answers. They will be on Blackboard if you want to look them over. But for the sake of time, I really want to get on to chapter 4. So we're going to skip those. Again, I'll post them on Blackboard by the end of the day. I have some meetings after class, but they'll be up eventually. No, I don't want to do that yet. So what we're going to do is we're going to move over to chapter 4. Chapter 4. Now I will say, and I meant to send out an email to the very specific few amount of people who it affects. I think there's 1 person in this class who it affects. There were a small handful of people who emailed me like a month ago for notes, and I sent you like all of the notes that I had up to that point, including the ones for chapter 4. I rewrote the notes for chapter 4 slightly. So there's a few things, if you have those notes in front of you, I think there's one of you, like this thing right here, this graph is not on those notes that I sent you a month ago because I chose to rewrite them about 3 days ago. The large majority of it is exactly the same. So sorry that you have slightly different notes. The main meat and potato stuff is exactly the same. You might just want to grab an extra sheet of paper and maybe tack some of the extra bits. But chapter. So chapter 4 is all about finding max and mins of a function. So remember that the derivative tells us slope, which again, I've been trying to remind you guys every 2 seconds. So derivative tells us slope, and it can also tell us where the function increases or decreases. And then remember that the second derivative tells us about the curvature of the function, how the concavity is. And remember, we wrote down this chart once before in our lives, and I said that it was going to be really important. We were going to use it a lot. Here's pretty much where it comes up. So let's rewrite that one more time. So if you forget, the chart I mean is that the fact that if the derivative is positive, the original function is increasing. The derivative is negative. The original function is decreasing. And then if the second derivative is positive, the first derivative is increasing, and the original function is concave up. And then if the second derivative is negative, the first derivative is decreasing, and the first derivative is concave down. The original function, I'm sorry, the original function is concave down. I'll give you 5 seconds to write that down. I think I said this before, but you guys are going to want to be pretty comfortable with these relationships and being able to go backwards, forwards, sideways. So these relationships are essentially going to help us discuss kind of the shape of the graph without needing the graph picture in front of our face. And specifically, we're going to use it to help us find maximum and minimum points of a function. So, definition. And I'll kind of leave that bottom part of that chart up just in case. So let P be a point in the domain of a function f. So it's just that it can be on that function. So f has what we call a local minimum at P. If f of P is less than or equal to the values at P for points near P. And I'll kind of explain the points near P in a second. And then f has a local maximum at P if f of P is greater than or equal to the values of P for points near P. So, hold on a second. So we have a function that looks like, you know what, let's add an extra curve there. There we go. So we have a function that looks like that. So essentially these 3 points here would be local mins. So local min, local min, local min. Oh, that one's lagging. There we go. And then these 2 points kind of at the peaks, if you will, would be local maxes. Local max, local max. Sorry, that second local max got a little squished. Now, notice that this particular local min in the middle is lower than the other 2 local mins. That doesn't matter, at least not right now. So to be a local max or min, that's what it kind of means by points near P. It just kind of has to be, you know, in a generic kind of interval around that point point is the highest or the lowest. So it's not necessarily the absolute lowest thing on the function or the absolute highest thing on the function. It's essentially just, is it the lowest or highest thing in a kind of interval around itself? So let me clean this back up a little bit, erase all those little thingamajigs. Also, the word relative can sometimes be used. Relative is sometimes used. So sometimes you'll see relative min or relative max instead of local. I believe your book and Wiley use local, which is why I wrote them as local. But just in case, they can be called relative as well. So yeah. Before I scroll down too far, I'll leave that up for a tiny bit. While I say, so the next thing says, consider the following function, the local extrema. Extrema is going to be a word to just mean maxes and mins. So if we don't really want to classify them as one or the other, we can call them extrema. Or if we just want to lump them all together and refer to them all at once, we call them extrema. So hopefully y'all have all that down. Say we have this function here, and this will probably be the last thing we get to. So I know the numbers are a little blurry. Sorry about that, but essentially every number you see is counting up by 1. So if you see a little blur, it's counting up by 1s. So say we want to estimate the x values at oh my lord, at which the value, nope, I can't read, estimate the x value at which this function f attains a local minimum. Well, the local minimum would kind of appear down here. So it would be at this point. So its x value would be 1. Again, sorry, it's a little blurry. So we would say this has a local min, and let's just say approximately x equals 1, just in case it's, 0.999 or something. What am I trying to write here? Local min, let's say x is approximately 1. I don't know what I just wrote there. Anyway, so let's say x is approximately 1, and again, just say approximate because we're not entirely sure yet. What value would the derivative have at that point? So remember, the derivative tells us slope, so what would the slope of the tangent line be at this point? Well, the slope at x equals 1, we could say that that is approximately 0. Again, let's say approximately, just because we're, going with approximate values here. So at that exact point that we're saying is probably that local min, we're saying that the slope is probably 0, approximately 0. And so what would the value of f prime be to the left and then to the right? So let me kind of consider the left side of this function before x equals 1 and then the right side after x equals 1. Well, if we look at that kind of piece there, that piece is decreasing. And if we go back to the chart that you have hopefully in front of your face because you took it down, if the original function is decreasing, the derivative is negative. So to the left, the derivative is negative. And maybe I'll even write f is decreasing to remind ourselves kind of why I came to that conclusion. And then what about the right side? Well, on the right side, it changes to being an increasing piece. So if we're increasing, what am I writing? Then the derivative is positive because f is increasing. So that's all that thing was asking me to figure out. And then we're essentially asked to look at the same type of idea, but with the local maximum. So the local maximum, appears back here, approximately at this point here, which seems like it's going to have an x value of x equals -1. So we're going to say that the local max, why do my x's keep looking like approximation signs that are too close together? We're going to say that x is approximately equal to -1 there. And again, we're going to say approximately because we're not entirely sure yet. And then the rest of it's kind of similar. So what would the slope of the derivative be at that point? Well, what's the slope of the tangent line at that point? Well, the slope at x equals -1 looks like it's going to be approximately 0. It's going to be exactly 0, but again, let's just say approximately. Well, then what's happening to the left and right of this point now? And this is where things are going to change a little bit. Well, if we look at the left side of this, we have an increasing piece for the function. So if the original function is increasing, what's our relationship to the derivative? Means the derivative is positive. And one of my screens is lagging a lot. Hopefully it pops up in a second. So to the left, the derivative is positive, since the original function is increasing. And then on the right side of the graph, the right side of -1, we now have a decreasing piece, so f prime is negative, since f is decreasing. So notice what we kind of recognize here, and what we're going to pull out in a second, is notice the difference between the left and the right kind of situations here. One of them changes from negative to positive, while the other one changes from positive to negative. And that's not a coincidence. That's kind of the point here. So we kind of see that at the min, to the left of it, the derivative is negative, and to the right of it, the derivative is positive. Whereas with a maximum, to the left, the derivative is positive, and to the left, the left, the derivative is positive, and the right, the derivative is negative. I think it's just notes next. So do I want to write down that? But we don't get to write that down until a little bit down there. So I'm going to take, you know what? No, we got a minute left. We'll just stop there, and we'll pick back up with this on Wednesday. Your quiz on Wednesday. So your quiz on Wednesday is going to be essentially another derivative quiz. So here's the function, find me the derivative, but it's going to be focusing on chain and product and quotient rules. So yeah. And at this point, we'll go ahead and end. If you have any quick questions, feel free to stick around. I do have a meeting in a little bit, but I can stick around for a little bit in case you have any questions. And otherwise, yeah, go ahead.
It's the homework problem that me and you did. It's chapter 3, section 3.3, and it's question 047. I can't figure that one out.
Let me stop recording.